Hello everyone, this is now part 3 of our series on modular arithmetic, and for today I'm going to be moving a bit further away from computations into using modular arithmetic as a filter to answer questions. Now when I say answer questions, of course I don't mean in the sense of solve problems because, well, I mean, we have already been solving problems, but answer questions like these. Now, in putting these here, some of you have already immediately had a good laugh if you are tuned into mathematical folklore. Basically, what I need to highlight is that it is surprisingly difficult to answer most of these questions. So most of the time, we are not really able to handle what we call Diophantine equations that easily. But modular arithmetic, basically what it can do for us is it just says no to some of these things. The thing about modular arithmetic is that it is very sensitive to the specific numbers, as we have seen so far. For example, if I'm doing something mod 101, I would use Fermat's little theorem, whereas if it's mod 100, I will split it into mod 4 and mod 25 by the Chinese remainder theorem, and then maybe use Euler's theorem. So very different character just by changing a number by 1. But what I have to say here is that modular arithmetic will allow me to answer A in the negative. That does not mean it can answer everything. So for B, it turns out the answer is yes. And very famously, I am actually looking at my phone right now because the answer is x equals to 8866128975287528. Y equals to negative 8778405442862239. And z equals to negative 273611146880740 is actually the smallest solution, believe it or not. Obviously, you're going to have the question, are you mad? How am I supposed to find that? With a computer. There is no way you can do this by hand, and so there is also no way that this can be asked as an Olympiad question. Right? So the answer is yes. But this is not a good question. Neither, of course, is part C. We are hopefully familiar with this to realize that this is just a rearrangement of Fermat's last theorem. Which, of course, tells me the answer is no, but the proof of Fermat's last theorem is a few hundred pages long. So we have to be, therefore, realistic. It is not that modular arithmetic can do everything. That does not make it useless. Just like if we get into a car can't fly. And if we get into an aeroplane, the aeroplane can't go into the sea. Now, that does not mean those are useless vehicles. It just means that they are used for a specific purpose. Now, in order to answer the question of, well, you said that it is not useless, how do I use it on this guy here? The answer is that I can use a particular modulo as a filter. So in my case, I'm going to use mod 9 as a filter. I'm going to use mod 9 to filter the cubes. And I will say that x cubed actually can only be 0, 1 or minus 1 mod 9. Which means that when you sum 3 cubes, you can only get from negative 3 to 3 mod 9, but 32 is congruent to 5, or negative 4, which is not in this list. The first question that some of you will then ask me is, how do you know that x cubed is only 0, 1 or minus 1 mod 9? The answer to that question is way more boring than you might expect. which is that I'm just going to check all of them. 1 cubed is 1, 2 cubed is minus 1, 3 cubed is 0. 4 cubed, 64 is 1 again. Now thankfully for us, we know that when we do modular arithmetic, everything that comes after will just be in reverse. So technically speaking, if these are all 1, 0, and minus 1, I don't need to check all the rest. So it's enough to stop halfway, and that tells me it is 0, 1, or minus 1. So the first question is answered. How do you know it's 0, 1, or minus 1? Well, you can check it here. The second question which you were asked then is, but why mod 9 and not anything else? And the truth is that some of it is just guesswork. But some of it also is going to be related to our knowledge of common go-tos. So for example, we will tend to use very often mod 4 or even just mod 8 for squares. Very often we will also use mod 9 for cubes. But this is not everything that we are possibly ever going to use. And we're going to see some examples here of how I will use modular arithmetic as a filter. With the caveat that please know this does not always work. For example, modular arithmetic would never ever be able to handle Fermat's last theorem, otherwise we would be done 300 years ago. Now here's an example from the SMO Senior. This is a round 1 problem, which may beg the question, but what's the point of saying the answer is yes or no to a round 1 question? Well, modular arithmetic says no most of the time. It doesn't actually say no all the time, which can be useful. In other words, it's just like if, let's say, you see a danger keep out sign because there is something that's under repair. Now the purpose of that is not to trap you, the purpose is just to redirect you towards the place where you can go towards. So modular arithmetic can serve that purpose. I'm going to try to find a reason why this usually fails. That's not the same as why this always fails, because that's possible but unlikely for a round 1 question. I want to know why this usually fails. Now, to understand why this usually fails, I want to take this whole equation, mod something, and say that it can't match up. At first glance, you might say, but what mod do I take? Well, if you did something like, let's say, mod 2, you're just going to get, this is odd, this is odd. So 1 plus 1 minus 0 is 0. Well, that is true, but that just means that I've discovered nothing. This is the problem of too general, or rather too easy to satisfy. Because it is usually the case that odd and even, either it clearly fails, which of course that would be good, but if it doesn't fail and it clearly works, that doesn't tell me anything. Now, the next thing you might think is, okay, well, how about mod 3 then? Because if I use mod 3, then the powers of 3 will be 0. Minus 8 becomes 1. The factorial is usually 0 unless n is 1 or 2, which we can deal with later. But the problem with this is that it doesn't really tell me that much, right? It just tells me that m is congruent to 2 mod 3, which is not nothing. This is if, of course, my n is not 1 or 2. But it doesn't really do a lot. So this is something that is, well, mod 2 is too easy because it doesn't really tell me anything. This one is too satisfiable. Now, by too satisfiable, it's because this m here is very flexible. Because 8m is just 8 times m. I can make m congruent to 0, 1 or 2 mod 3, then 8m will be also 0, 1 or 2 mod 3. So how do I sort of explain why this usually fails? I want to get rid of the flexibility, and so I'm actually going to take mod 8. Because if I take mod 8, this is gone, this is also gone, and powers of 3 mod 8 are just 1 and 3. So essentially, 4n factorial is also going to be 0 mod 8 unless n is 1. So unless n equals to 1, my equation is going to go 1 or 3, 1 or 3, and then 0, 0, 0. Maybe I should not cancel away my question, but 0, 0, 0, that's not going to happen, right? Mod 8. Which leaves me with n equals to 1. And that's the whole point of modular arithmetic. It can kill off almost every possibility. So n is equal to 1. It's the only place where things may work. If I put in 1, then I just get 3 to the m minus 8m is equal to 681. It is now quite obvious that for the left hand side, powers of 3 are going to increase really fast, so you just find a nearby power of 3 and hope it works. So if we just list out the actual powers of 3, 729, which is 3 to the power of 6, is near enough, and m equals to 6 actually works. So m equals to 6, n equals to 1 is going to be the only solution, and mod 8 has helped me to fish this out. I've used the term fishing. This is also going to be one of the things that is a useful analogy. When you go fishing and you cast the rod down, or you cast the net down, you don't cast the rod down or the net down knowing with 100% certainty that it is going to catch a fish. You cast a rod down where you think you have a decent chance of catching a fish. And if you catch the fish, you're happy. If it doesn't work, you reel in the line and then you say, oops, okay, let me cast the rod down again. And you try again and again. Obviously, this is not something you try forever. How long do you want to spend trying this approach is something that is a quiet skill. So I can't really tell you when, but certainly it is like a 30-second to 1 minute attempt when you use, let's say, something like mod 8, something like mod 3, so we can afford to attempt quite a lot of these. They don't take too long. So here's an example from the Bangladesh Math Olympiad this year, where now P and Q are prime numbers. And I have P cubed minus 3 to the power of Q is 10. And I think, of course, that when I see a question like this, most likely the answer is going to be not too many. Otherwise, how am I going to find it? But what more do I take? If you say that I'm going to take mod 3, that is not going to be enough, because P cubed congruent to 1 is definitely possible. And if you took mod 9 and say that, oh, mod 9, then 3 to the power of Q is going to be a multiple of 9 as well. Well, that indeed is true, but P cubed congruent to 1 is still possible, so I have not really learned that much. Okay, so then you might say, okay, but what about if I take mod 27? Well, that leads to a bit of an annoying situation of, okay, so you're telling me that if Q is greater than or equal to 3, now I've got P cubed is congruent to 10 mod 27. Can that happen or not? Well, mod 27 may take a while, you see. So if I take 1, 8, 27, 3 cubed is 27. Then after that, 64, well, that is 10. 4 cubed is 10 mod 27. So I've not learned anything. This does not mean the answer is P is 4, clearly. It doesn't even mean that P is 4 mod 27, because there could be some other thing that gives me 10 mod 27 when I cube it. So this is not going to work either because, now I put a tick here means that it could happen, and that's not good. I'm looking for something that will make it fail. Now I might try it and say, okay, how about if I take mod 10? But definitely it's possible for the last digit of the cube to be anything you want and to match the last digit of 3 to the power of cube. So that's not going to be informative enough either. Well, one way that can guide us towards what to do is just to simply say, I will try to find one answer and use that to gain some information. Now we are supposed to have 3 to the power of q plus 10 be p cubed. So let me just write down powers of 3. In fact, I've already just written down powers of 3 in the previous question. Let me just write down a few more. And I'll just look at when I add 10, do I have a cube? Now, of course, I wrote all of this down, but take note that because you're looking at primes, this is 2, 3, 5, 7. Actually, I only need to look at these 4. The next one is 11, which I don't feel like calculating, right? So that's why I stop here. Actually, you will clearly rule out 19, 37, and 253 is also small enough. A bit of checking will tell us that, oh, 2197 is 13 cubed. So I found a solution. Q equals to 7 and P equals to 13. But you might say, okay, then do I want to test some more? In the SMO round 2, sure. But so that this video doesn't end up being 1 hour long, let's not test some more. Let us just fast forward the process by using this as a bit of a clue. Now, I always want to try to find a reason why it usually fails. And so, I think that mod 13 is an interesting choice. Why? Because the only prime divisible by 13 is 13. Which means that P is 0 mod 13 is a unique thing. If let's say I did something like mod 5, P could be 1, 2, 3 or 4 mod 5 many times. And so that doesn't restrict my solutions enough. But if P is 13, that's the only time it will ever be divisible by 13. I'm not doing mod 7 because 7 is in the exponent, so that doesn't actually tell me that much either. Okay, so let's try mod 13. Now, in mod 13, I basically looked at this P equals to 13, which is 0, but what else is there mod 13? So 1, 8, 27 is also 1, which is interesting. This is actually minus 1. So I've got 1, I have 8, I've got minus 1. This is also 8. And this is also 8. So very good. I've actually just discovered that obviously there's always 0, but 0 is the exception, right? So it's 0, 1, minus 1, and 8, which is a surprisingly short list of possibilities. And let's try it on the left hand side. But actually we've already seen that 27 is 1, right? So which means that this is just 1, 3, or 9. Now a very quick check will tell us that 1 plus 10 is 11. Does not exist here. 3 plus 10 is congruent to 0, exists. And 9 plus 10 is congruent to 6, does not exist. So only this one works as a way of satisfying it mod 13. Which means that, of course, P must be 0 mod 13. The only cube that is divisible by 13 is a multiple of 13 cubed, or 0 mod 13 cubed. So P is really 13, and this is going to be the one and only pair that works. So there's a little bit of meta gaming involved in figuring out what to take the mod of, right? The first meta gaming aspect is that I trust that you're not going to give me something like this that actually has a solution that looks like this. So it must be small. And if it must be small, or maybe the few solutions, plural, are small, then there must be a reason why big ones don't work. And if big ones don't work, maybe it is because when things are big enough, that particular choice is no longer available to me. Now, here's another question. This is from the China Northern Math Olympiad, which is going to involve the same kind of idea. And if you are attentive to what we've just done, you would realize that, of course, I'm still using this 3 to the power of x. There's no need for it to be 3, right? This is just coincidence. But I'll let you think about how we could handle something like this. So I'll leave this as an exercise which you can think about the modulos we have already used. Do they work? And also, you can think about whether you can use the philosophies we have taken so far, which is that look for something that reduces the flexibility and also use a small solution that works as a launch pad for you to figure out what mods to take. Now, I just want to end off this video with a question from the junior round 2 a couple of years ago, just to point out that this modular arithmetic filter is useful in a lot of other ways that you will continue to discover. The fact that, let's say, a power of 3 can only be 1, 3, or 9 mod 13 may be useful in more situations than you think. The fact that, let's say, a square can only be 0 or 1 mod 4 is possibly more useful than you think. But essentially, every single time when I see a quantity, there is going to be a list of values it can take on modulo whatever. So for example, if I had the factorial just now, the last digit can only be 1, 2, 6, 4, and then it becomes 0 after that, right? So this is the list of things it can be mod 10. Now, there will always be such a list, and so it is going to be likely that if you want to show that something cannot happen or something must always happen, it may be that you can show that this is going to fall into the thing that will never happen, and therefore get some nice conclusion. And I'm going to use this for this question here. This question here is pretty nice because it is also an example of how modular arithmetic can come in later in a problem. But why are we even thinking along these lines is that there is a mention of positive integer. Now, there is a mention of positive integer, which means that we are in the land of number theory. Because obviously, if I have got this is the fractional part, and if n were not an integer, I could just let n be 1 over square root 19 and the left hand side will be equal to 0, right? That would just kill it off immediately. So, my thinking is that why is this always going to be greater than 1? It must be that if this is small, then this must be big enough. Now, how would this be small? Well, this would be small if n root 19 is very close to an integer, but just a little bit. So I'll just call it like m plus epsilon, where epsilon is then going to be something small. How small can the epsilon be sort of depends on if I now square this. Which is just m squared plus a bit. Because epsilon, again, you want it to be very small and discover what happens. Well, if it is m squared plus a bit, that means that I'm asking 19n squared minus m squared, is that a bit here? How small can this be? Well, this is definitely an integer. Now, this cannot be 0, right? Because of the fact that obviously m squared equals to 19n squared doesn't work, because that would mean m over n is square root 19, but we know that square root 19 is irrational. So then I would ask myself, okay, can it be equal to 1? And this is where the modular arithmetic can come in. That if I were to take mod 19, this is saying that m squared is congruent to minus 1. Well, in fact, let's look at what the squares can be mod 19. 1, 4, 9, 16, which is negative 3, 25, 36, this is negative 2. And then of course we know that once we reach 10, 10 is negative 9, so it loops around. And the closest you get is negative 2, but not negative 1. And so therefore, this is at least 2, if it's positive of course. And that is really the crux of this entire solution already. The crux of the entire solution to this question is the fact that 19n squared minus m squared is not as small as we think. Now, let's come back to the problem itself, and I'll just show you how this argument is going to translate. Okay, so I think I don't really need this for now. I will just erase it first. But remember what we've just said. So I'm saying suppose this is very small. So I'm going to I'll let x equals to n root 19, so that I'm now looking at x times the fractional part of x. Well, so suppose that it's not. Obviously, since this is a positive integer, I don't have to worry about it being negative. So suppose that actually this is between 0 and 1. Well, the 0 is a bit negligible, so I'll just not write it there. So this is saying that my x is less than or equal to 1 over this fractional part, or maybe let's just write it as this 1 over the, put the fractional part here. I don't want the fractional part in a fraction, that just confuses me a bit. So assuming that this fractional part is quite small, now of course if the fractional part is quite small, this is related to x itself. I can add back the integer part in order to make x appear, which is what I would prefer to do. So I'm going to write it like this. Of course, if you want to put this here, you can. And because I would like an integer, I'm going to sort of rearrange this and say that this is also the same as if I say that my floor x is close enough to x. Okay, so this is the algebra part. I've set up the algebra how I want it. I wanted it to be now something that I can square. And I want to square it because if now I square both sides, well, actually there's all sides, if you will. Remember, of course, that I was going to square this the whole time and talk about how close another square can be to it. So this floor of x was always that m that I wrote just now. Well, this can happen only if x squared minus 1 is here, because this is slightly more than x squared minus 2. So floor of x squared is an integer, it must be therefore x squared minus 1 or x squared. Now x squared, which is what we've been waiting for the whole time, is in this range. Which means that I'm just claiming that this square, which I called m squared just now, it cannot be equal to 19n squared. It also cannot be equal to 19n squared minus 1, and that's a contradiction. And this exact argument here will tell me what would be a quite close shave, right? Which is that I've seen this 36 is negative 2. So if I were to have made my value to be quite close to that, or something else that is quite close to that, you may actually be quite tight. And so if you tried, let's say n equals to 3, you will find that this is very close to 13. This is something quite small, and so it is just about going to fit into the greater than 1 because of the fact that your 13 squared is negative 2 mod 19. That's the closest you're going to get. And if I were to change the number to something other than 19, where it is possible to get negative 1 mod that thing, like let's say 17, it would not be true anymore. And that's the beauty again of number theory and modular arithmetic. Exactly how big the number is and how small the number is, and whether is it odd, is it even, is it 1 mod 3, 2 mod 3, all of these things can potentially matter. That's where I'm going to conclude this video. Hopefully you see how we can also use modular arithmetic as a tool for round 2 problems. And I'm probably going to take a slight break after this for Christmas, and when we are back, we'll be looking at a further advancement of our modular arithmetic, where we'll talk about the previously advertised order as well as possibly something like quadratic residues. Thanks for watching, and see you again at the next one.